Let's get started. Good evening, everyone. Welcome to Steward Observatory and the Steward Observatory Public Evening Lecture Series, which began in 1922. And we're very happy that we've been continuing to offer these lectures since 1922. There are seats up front if you need to find a seat, please. And we welcome those of you who are watching this podcast on the internet at www.as.arizona.edu. Well, I can speak a little bit less louder, but it's only me for a little bit, okay? All right. So, before we begin with tonight's speaker, I want to move over to show you a change in our Okay, I really moved it down now. All right. We have a very busy month of March scheduled for you. Next week, we were supposed to have this conference on DESI, which is an instrument at Kitt Peak. Oh, there are seats down here. We can't allow you to stand back there, please. There are seats down here. Seating is first come, first served. There's no saving of seats. So please come down and take a seat, all right? Please come on down. And we have seats over here as well. Thank you for coming. So, and some of the guests were going to give a public talk on Monday night. This morning they canceled because of the coronavirus. They decided to cancel the meeting. However, one of the scheduled speakers is local. She works across the street at what used to be called NOAO. Now it's called the NSF OIR Lab, but it's Kitt Peak, okay? And she's going to still give the talk. So we'll still have that talk next Monday, and it's spring break here at the university. So you can't expect anything at the student union to be open or anything, but you'll have easy parking. 2 weeks from tonight, our Bach fellow, Cristobal Petrovich, will give, every semester we have a talk in Spanish. So he will be giving his lecture in Spanish, Sistemas Solares Extraordinarios. Vivian Miranda will be here on March the 30th to talk about cosmology. I'm still trying to find a speaker for April 13th. I'm not having luck. I'm trying to find someone at LPL to talk about a planetary science topic, solar system topic, so I'm still working on that. And then finally, it turns out on the 24th of April in 1990, can you remember that long ago? That's when the Hubble Space Telescope launched. So we're coming up on the 30th anniversary, and Professor Roger Thompson wanted to, we already had 50th anniversary of the discovery of the molecular cloud and the shutting down of Spitzer. So we're going to have a 30th anniversary talk from Hubble Space Telescope to round out our semester. There are plenty of seats down here. Yeah. Please sit. All right? So, without further ado, it's cloudy, and it's probably going to rain tonight. So unfortunately, the telescope is not open, all right? But if you're here for an assignment, at the end of the question and answer period, I'll be right at this table to stamp your assignments for students that are here for a talk. So, we're glad to finally have Kate Grier here, okay? Dr. Catherine Grier, you remember, was supposed to speak to us last November, and we had to postpone her talk. Catherine Grier is, she's kind of a Big Ten kind of gal, okay? She received her bachelor's degree in astronomy and physics from the University of Illinois, Champaign-Urbana, right? She received her PhD from the Ohio State University in astronomy. And then she did a postdoc at Penn State University, which is also now a Big Ten school. But they don't know how to count in the Big Ten, right? So, and then she is now here as a postdoctoral fellow at Steward Observatory. And she is going to tell us about the monsters of the universe, supermassive black holes and their masses. Kate.
All right, thank you. All right, can you guys hear me up there? This doesn't sound like it's on.
I have it on.
Yeah, it is on. Okay, just start
It is
talking.
on.
Okay, hang on. I'm going to fix this again. Okay, how about this? Test, test, test.
Start talking.
Testing? Okay. All right, thank you everybody for coming to my talk tonight. I am going to be talking about a topic that is dear to my heart that I have been working on ever since I started studying astronomy. Can you guys hear me okay in the back now? We're good? Okay, good. Okay. I'm going to start off with a little bit of an introduction to just black holes in general, but most of the talk is going to be focused specifically on supermassive black holes. Does anybody, this is a little bit fuzzy up on here, does anybody recognize this little blurry blob? Yeah? All right, this was quite a big deal last year, so I'll go through and definitely talk about our little fuzzy black hole blob here too. So let's go ahead and get started. So first off, just a basic definition of a black hole. A black hole is an object that is so dense that there exists a region in space where its escape velocity is faster than the speed of light. Okay, so there is a point where you can, if you get close enough to a black hole, where not even light can escape. And that is just the very basic definition of what we consider a black hole. Now, in order to really understand what that means, we need to understand what the concept of escape velocity means. Okay, so the escape velocity is the velocity or speed needed to break free of an object's gravity. Okay, so let's say we wanted to launch something off of the Earth, as we have in our little diagram here. So here's a little cannon. It's going to shoot off something parallel to the surface of the Earth. That doesn't really matter too much in this talk, but if we launch something very slowly, it's going to travel a little bit and then fall onto the Earth, okay, due to the Earth's gravity. If we launch it a little bit faster, it'll make it farther before it falls. If we launch it even faster, we can actually send it into orbit around the Earth. Okay, it'll continue to fall, but if it's going fast enough, it'll end up going in a circle. But at some point, if we get fast enough, we reach its escape velocity, and that will send it all the way away from Earth. So in order to get something off of the Earth, we need to send it moving pretty quickly. And so everything in this universe that has gravity, which is pretty much everything, has an escape velocity. Okay, we're made of mass. We have escape velocities. Okay, now we're not very big, so our escape velocities are not very big. But here's a few examples of the escape velocity for a few different objects that we have. So the Earth, in order to get something to leave the Earth, we need to shoot it off at about 25,000 miles per hour to escape the pull of the Earth's gravity. Okay, and as we get toward bigger and more dense objects, we need higher and higher escape velocities. And so the definition of a black hole here is that the escape velocity from the sort of surface, if you will, of a black hole is the speed of light. And that's actually how we define the surface of a black hole. We define it as the point away from the center of it where the escape velocity is equal to the speed of light. Okay, and that's around 670 million miles per hour. Now, the more dense the object, the higher the escape velocity needed. So in order to make something more dense, you either need to add more mass, you need to add more stuff to it, or you need to squish it down and make it smaller. And so essentially what a black hole is enough stuff, enough mass, that has been squished down so that it's so dense that there exists this what we call the event horizon, okay, where nothing, not even light, can escape its gravitational pull. Now, another way to think about this is everything that has mass has some effect on space. Just the space in outer space is bent around anything that has mass. And so the more mass, or the more densely packed the mass is, the more of an effect it has on space-time. So if you could kind of envision it as like you have a little rubber sheet that you've put a ball in the middle. Okay, if you have something that's really tiny, okay, that rubber sheet that you're holding out will sort of dip a little bit, but it doesn't really warp your rubber sheet very much if it's not very heavy or if it's spread out over a really large area. Okay, but if you start to put something heavier, like a bowling ball or something like that, in a little rubber sheet, it'll start to warp the space-time here. And so anything that's traveling or trying to get across that space-time has to deal with that warp. It has to deal with that distortion that's caused by something that has mass. And so what we do with a black hole, essentially, a black hole is an infinitely deep little well that we put something infinitely tiny, but infinitely, not infinitely massive, excuse me, something with mass that's infinitely tiny, and it creates, essentially, you kind of think of it like a little hole. And so everything that tries to cross across here, falls in and can't get back out. And since nothing we know can move faster than the speed of light, that means that nothing we know can escape the pull. So how big is a black hole? So a black hole doesn't really have a solid surface. So usually when we're talking about the size of a black hole, we're talking about the size of its event horizon. Okay, that point, that distance from the center of the black hole where the escape velocity is equal to the speed of light. Okay, so there's no solid surface there, but that's the point where light can no longer escape. And so the event horizon of a black hole that has 3 times the mass of our sun is about as big as a small city. Okay, so a few kilometers, give or take, depends exactly on how massive it is. But the size of the event horizon depends just on the mass. So larger masses give us larger event horizons. And so once we start talking about bigger and bigger black holes, you'll see that we can get black holes that are sort of on the size of our solar system. So if the Earth, for example, was the size of a small marble, okay, it would become a black hole. If we took the Earth and we squished it down, we kept all of the mass on it, okay, we didn't remove anything from it, we just squished it down in size to about the size of a small marble, it would become a black hole on its surface. So that means that the surface of that marble would be, the escape velocity from that surface would be equal to the speed of light. So now this starts to bring me to one of the largest myths about black holes. Okay, everyone's always very, very concerned about black holes and what effect they might have on us. So the myth is that black holes will eventually suck everything in because nothing can get out. So it seems sort of like it makes sense that they would just keep pulling everything in and we would all just, eventually everything's going to go in and go dark. But the truth is that black holes really only act funny when you get close enough. Okay, if you're far enough away from a black hole, it just acts like any other thing that has mass, like a star, for example. So if we, for example, were to take the sun and keep its same mass, so keep the same amount of stuff in it, and squish it down to something maybe 1.5 miles across or so, maybe a little bit bigger than that, it would become a black hole. And at our distance from it, at the distance that the Earth is from the sun, we would just continue orbiting just like normal. Okay, nothing would happen as far as falling in. Now, it would be problematic for other reasons because we rely on the sun's light for life on Earth. So that would be a problem. But we wouldn't fall in because we are far enough out that it just acts like any other object that has gravity. So any other sun. So things like the supermassive black hole at the center of our galaxy, we are very far away from that. We're far enough out that we don't have to worry about any weird black hole effects. Now, once you start getting close to a black hole, you do have what we call general relativistic effects. Okay, things start to get a little bit wonky when you get close in, because what happens is as things fall, they start moving faster and faster because the black hole's pulling so strongly on them. They start to move very fast. And so things that start to get close in, even before they hit the event horizon, time and space start to go a little bit funky. But again, we're far enough out that we don't really have to worry about that. So there's a couple of different kinds of black holes that are talked about frequently in astrophysics. The first are stellar mass black holes. And these are black holes that are formed when massive stars die. So if you get a star that's, I think, on the order of 8 times the mass of the sun, or bigger, when that star dies, when it runs out of fuel, okay, it is possible to collapse down into a black hole and leave a black hole behind. We see these sprinkled throughout our galaxy as objects that are called X-ray binaries. So what happens is, if you have a star that has died and become a black hole, if it's close enough to another star, it can start pulling material off of that nearby star. This nearby star has gotten too close to the black hole. Okay, it starts to pull stuff off, and that material kind of spirals in and forms this disk around the black hole. And that material gets really, really hot as it spirals in. It eventually falls in, okay, but while it's spiraling in, we can still see it because it gets really, really hot and it emits X-rays. And so we can actually see these with X-ray telescopes as X-ray sources. And so we've observed many throughout our galaxy that are in areas where we think there was once a massive, really massive star that once lived. So there's actually a famous X-ray binary, one of the first ones that was confirmed in the constellation Cygnus. It's called Cygnus X1. And we're pretty sure that that one has a black hole in it. So again, the region around a black hole where you really have to worry about things is actually very small compared to how big space is. So these black holes, these stellar mass black holes that are sprinkled throughout our galaxy, are also not really a cause for concern. Now, if we had a nearby really massive star that was very close to our sun, that we thought might eventually turn into a black hole, that might eventually become a problem. But we don't have anything that's close enough to us that we have to worry about something like this. So those are stellar mass black holes, and that's actually an entirely different area of astronomy than what I spend most of my time talking about. And so next I'm going to move on to supermassive black holes. All right, so supermassive black holes have masses of thousands to billions of solar mass, tens of thousands or so, to billions of solar masses. Okay, so we're not just taking one star that explodes and leaves behind, 3 or 4 solar masses inside a black hole. We now have hundreds of thousands to billions of solar masses. These objects exist at the center of pretty much all massive galaxies. Okay, so there are millions and billions of them out there, and they are thought to be the powerhouses behind the phenomena known as active galactic nuclei, or quasars. And I'm going to come back to quasars and active galaxies in a little bit. But first, these 3 images that I'm showing here are just examples. So this here is our famous image of the supermassive black hole in the galaxy M87. And this middle image here is a galaxy that hosts the largest black hole that has ever been found. It is 21 billion solar masses. So it is a monster. And this, some of you might recognize from the movie Interstellar. This is a simulation of what a supermassive black hole might look like in certain types of light that they produced for the movie Interstellar. And it was really a very stunning, beautiful simulation, and it was done as physically accurately as they could. And they didn't even have to spice it up for the movie at all. It just turned out that it looked really cool, just the way it was. So it was kind of neat that they did that. So to start off the talk about supermassive black holes, let's talk about the Milky Way. Okay, we have a supermassive black hole at the center of the Milky Way, and it's about 4 million solar masses. So it's not as big as that giant from the last slide, but it lies at the center of our galaxy in the constellation Sagittarius, and so it's named Sagittarius A star. And this image here is a combination of X-ray and infrared, and it's zoomed in toward the very center of our galaxy. So the infrared is in red, and the blue are X-rays. And if you zoom very close into the center of our galaxy, you can see that there's a bright X-ray source. And there's not many things that produce large numbers of X-rays naturally in the universe. X-rays, you have to get something very, very hot to produce X-rays in our universe. And so this is one of the first indicators that we have a supermassive black hole there. But the cool thing about Sagittarius A star is because it's in our own galaxy, we can actually see the stars moving around the supermassive black hole. So I'm going to show a little animation here. I'll show it a couple times so you can get a sense. But what this is This is going to be a time lapse of the motion of all of these stars here. And this plus sign is the location of the supermassive black hole. This is an infrared image, and you'll notice that there's nothing behind that plus sign because we can't see the black hole itself. But if you watch, let's see if I can get it to play. There we go. You might notice that you can watch some of the stars kind of zip around this empty region in space. So we're going to zoom in now. Okay, so that star sort of curved around, but this star in particular, if you follow it around, you can see it zip around. All right, and stars just don't do that on their own. They have to have something making them zip around in an orbit like that. So let's watch it one more time. It's kind of hard to know what to look for until you've seen it once. And you can see this covers about 10 years. Okay, so this took about 10 years to produce. But if you track the orbits of these stars, you can see they zip around this empty region in space. And it turns out you can use the motion to determine, and some actually fairly simple gravity laws, to determine how much mass has to be in there, just by looking at the orbits. So if we look at the orbits of all the stars together, okay, you can see that there's this common focus. Okay, there's this point right in here that seems to affect the orbits of all of these stars at the center of the Milky Way. And this is how we know that there is a supermassive black hole in there. Because in order to make these stars do what they're doing, there has to be 4 million solar masses in this region. And we know that we can't see anything very big in there. So we have sort of an upper limit as to how big that thing can be. And so there's only one thing that can have 4 million solar masses and be that tiny, in that tiny region. And that's a supermassive black hole. So it's really cool that we can do this because it turns out that the region over which the black hole has an influence like this is really, really tiny compared to the size of a galaxy. So we're looking at the very, very center of the galaxy here. And galaxies have billions of stars, and galaxies are actually a lot more massive than the supermassive black holes that live in them. And so if you go farther out, you can't really see this effect as well. You can only see it very close in. And if you go to other galaxies, it's actually we no longer have the ability to resolve these individual stars. So we can't plot individual star orbits. And so we can't, it's a little bit harder for us to figure out. And so when we're looking at other galaxies, we have to use slightly different means to figure out what's going on in there. So these galaxies are too far away to chart the positions of individual stars, but we can actually take the velocities of large populations of stars and large sort of clumps of gas toward the very center of these galaxies. And we can use those velocities and those measurements to determine how much mass has to be in there. So it turns out that in pretty much every galaxy that we can do this with, the motions of the stars and gas also indicate that there's something really tiny in the middle that we can't see, that is not bright enough to overwhelm all these other stars, but it has millions or billions of solar masses inside of it. And so that's how we know that there are supermassive black holes inside other galaxies as well. So until very recently, this was sort of the best evidence that, at least the best solid image evidence, I guess, that we had. So being able to measure the velocities of the stars and gas in there and measure how fast they're going was the only way for us to really tell that there was a black hole. But recently, last year, the Event Horizon Telescope collaboration had a look at the supermassive black hole in M87. Okay, so this is M87. This is a Hubble Space Telescope image of the galaxy. You can see here it has this is only part of the galaxy. So we're looking at a very zoomed in image of the center of the galaxy. You can see it has a very bright center. You can also see it has this little jet coming out. Okay, that's another common feature of something that we call active galaxies. And if you zoom very close in, we see that it has this really bright, what we call an active nucleus. And so the Event Horizon Telescope collaboration pointed all of their resources at M87 in order to try to resolve this. So this region is very, very tiny. And again, the size of a supermassive black hole compared to its galaxy is very small in angular size on the sky. Okay, we're talking about something that, in order to be able to see the black hole itself, the shadow or the lack of light, we need to be able to see something that's on the order of tens of micro arc seconds in angular extent on the sky. So exactly how small is that? So if you hold your hand out or your arm out at arm's length, your pinky is about 1 degree. Okay, 1 degree in angular extent. So an arc second is 1/3600th of your pinky. Okay, and a micro arc second is 10 to the minus 6 of that. Okay, so that is what the kind of resolution that's needed in order to be able to see the event horizon around a supermassive black hole. And until recently, it just hasn't been done. Okay, and so last year, the Event Horizon Telescope, they took telescopes from all over the world that were set up for this purpose. They pointed them at M87 at the same time, and they used what we call interferometry, okay, where you can take telescopes from the smaller telescopes that are spread out by large distances, and you can combine their signals to get a better resolution. And so this made the front page of the New York Times last year. This is the very first image of a supermassive black hole. This one's a little bit fuzzy, so let's move to this one. Now, they all look a little bit fuzzy. But essentially what you're seeing here is material that's about to fall into the black hole, okay, material around the black hole, and this shadow at the center is about 3 times the size of the event horizon. So the event horizon of the black hole is really here in the middle, right in here. And this is the first time that anyone ever has been able to get even close to resolving and seeing this black hole shadow. And it turns out that everything that they saw was pretty consistent with theoretical ideas of what a supermassive black hole would look like according to general relativity. And so everyone was very excited because there's still a lot of people who like to say, well, you haven't seen one, so, you know, how do you know they're really there? And I mean, we're never going to be able to see anything in there because light can't come out of there. But this is as close as we can get to seeing something like this. And I like this particular version of it. This is from XKCD because they show how big the solar system is relative to the size of this supermassive black hole. So we now have millions of solar masses that are squished inside the orbit of Pluto. So instead of like our solar system where we just have a single solar mass squished in there, we now have millions of solar masses in there. So it's really a very cool thing, and we were very excited to see that they were able to start doing this. And I believe that they have their sights set on the Milky Way black hole as well. So I'm hoping that sometime soon we will also hear some news, I have no idea when, but some news that they've been able to do this same thing with the Milky Way's black hole. They actually, I believe they looked at it before, but they had bad weather at some of their telescope sites. And it takes so much energy and effort to coordinate all those different telescopes at the same time. If one of them has bad weather, then the whole thing can be shot. So hopefully we'll get another image like this soon for the Milky Way. So how do you make a supermassive black hole? This is actually a topic of concern among astronomers. It's actually very difficult to make a supermassive black hole, but one of the main things that we think happens along the way is we have large galaxies that have black holes at their center, and they merge together. Oops, that's not what I meant to do. I'm going to play this. There we go. So this is just a little simulation of 2 black holes that are starting to get too close to each other. They eventually spiral around each other and get closer and closer and closer. As they get closer, they emit gravitational radiation, gravitational waves, if you will, which is now also something that we can detect. and eventually they spiral together and merge into one larger black hole. Okay, so the idea is that we start with a lot of smaller black holes. We collide galaxies together. We collide their central black holes together to build bigger galaxies, or to build bigger black holes. And the reason we can't just have the black holes eat things, okay? It doesn't work to just have a black hole slowly growing by eating things. The problem with that is we actually see supermassive black holes very early on in the universe. And I'll come back to how we see that in just a minute. But we see supermassive black holes that have millions to billions of solar masses less than 1 billion years after the Big Bang. Okay? And there's actually not enough time to grow a supermassive black hole just by eating stars and gas during that time. This is actually still a problem in astrophysics, trying to get black holes to be big enough, early enough on, that we can make things work. And so it turns out we have to have these mergers of black holes that are already a little bit substantial in size in order to actually build these black holes big enough. So what happens when something comes too close to the supermassive black hole? When a star or a cloud of gas or something like that comes close, it starts to have what we call tidal forces that act on it. And what happens is parts of the star, as the star is going to come back around, you'll see what's happening here. Parts of the star are closer to the black hole than other parts of the star, and so they get stretched out and sort of ripped to shreds. And so the stars and gas get pulled into these large, pulled apart, and the material starts to spiral in. And for a short time, you have this disk of material that spirals into the black hole. And eventually, once that material is eaten up, then that disk of material disappears. Okay, so that's the basic idea behind how we more slowly grow a black hole. Okay, rather than just smashing them together, they can also eat nearby things that get too close. And we sometimes see this with the Milky Way black hole. Sometimes a cloud of gas or something will wander a little bit too close to the black hole in the Milky Way, and it will flare up in the X-rays for a while because that disk of material, you can watch it one more time, that disk of material gets very hot as it spirals in. And so we can actually see, when that happens because we get these flares of radiation before the material falls in. So as the star comes back around, you can see it gets ripped to shreds, and then all that material spirals in, continues to fall in, and makes this disk of material. So that's how we feed a black hole. And in galaxies like the Milky Way, we see these sort of blips when something happens. We see something wanders too close, and we get a burst of radiation for a while. But there's also a class of objects that actually have a constant flow of material falling into them. The Milky Way is referred to something that we call a quiescent or a normal galaxy, because its black hole isn't really doing very much other than occasionally sort of eating something up that wanders too close. But we have another whole set of objects that are called active galactic nuclei. Okay, and so if the center of a galaxy is unusually bright, we call it an active galactic nucleus or an active galaxy. Another word for the same phenomenon is a quasar. Okay, but quasars are the more luminous, the brightest examples of this phenomenon. This example is M87, so this is the one that they imaged. You can see this is actually an optical image with a radio jet coming out. And so these are all stars coming in here. But you can see the very center of the galaxy is brighter than the stars around it. So when you have an active nucleus, the very, very tiny center part of the galaxy can outshine the entire rest, the billions and billions of stars that are in the whole rest of the galaxy are outshined by just this very, very center part. And when we look at a quasar, okay, So quasars were first discovered in the 60s when they found something that looked like a point source. It looked like a star, but it was very bright in radio wavelengths, and its spectrum, so the color of radiation that came from these objects, did not look the same as stars. So they were clearly something different, but nobody really knew what they were. So they gave them the name quasi-stellar radio sources, because we got radio emission from them, and they kind of looked like stars, but they kind of don't. And so people were really confused because instead of seeing this bright, beautiful galaxy like over here, we actually have just this tiny little point. But this tiny little point is actually an entire galaxy that's far enough away that we can't see. Okay, we can't resolve the stars and the material around it. But the center of it is so bright that we can see it anyway. Okay, so the center is just extremely bright. And so, so what we have going on here is we actually have a galaxy with a supermassive black hole at the center that has a disk of material falling in. But unlike the Milky Way, this disk is pretty much always there, at least as far as our lifetimes are concerned. So this disk of material, as it spirals in, gets very hot and gets really, really bright. And so we can see the very, very center of these galaxies outshining the entire rest of these galaxies. And so if you ever see something referred to as an active nucleus, active galactic nucleus, or an AGN, or a quasar, that's essentially what you are looking at. So the cool thing about active galaxies, or quasars, is that we can see them across the whole spectrum of wavelengths. So we can see them all the way from the radio all the way up through the X-ray. And so the idea is that the gas that is closer in gets moving faster and faster and gets hotter and hotter. And so the inside of the disk gets very, very hot, and so we have things like X-rays coming from very close into the black hole. And as you move farther out in the disk, we have lower energy radiation coming out, where we have light from the ultraviolet and the optical. And even farther out, we also see infrared. So we see the whole range of wavelengths. And so it doesn't matter what kind of telescope we look at an AGN with. Most of the time, we can see something. So this indicates to us that they have this wide range of temperatures, and that's how we know that they have these disks. So most of the stars and other more common things sort of emit a lot in sort of the ultraviolet, visible, and maybe the infrared. But we have light across the entire spectrum coming from active galaxies. Now, another really useful feature of quasars is they're super luminous. They are really bright. And this means that we can actually see them across the entire observable universe. So the most distant quasar known is on the order of 13 billion light years away. Okay, that means that when we look at that quasar, we are observing that quasar as it was 13 billion years ago, because it took that long for the light to travel to us. So quasars and active galaxies give us a way of looking at the universe when it was very young. Okay, now stars aren't bright enough for us to be able to see them when they're that far away. And even a lot of normal galaxies, okay, are difficult to see that far away. So quasars are unique in that they can allow us to look back and get an idea of what was happening in the universe. And so this is why I say, this is what when I said that there was an issue with supermassive black holes being too big too early. We have, this little blip here is actually a quasar that has millions or billions of solar masses in it, and it already exists less than 1 billion years after the Big Bang. And so any theories or simulations that we do, that we create that explain how galaxies and supermassive black holes are formed has to account for that. So what turns a galaxy into an active galaxy or a quasar? We're not 100% sure, but there's probably a number of factors in it, but there is one common thing in that we think that that we see that some galaxies, when we're able to see the galaxy around a quasar, these galaxies look kind of disturbed. They're not these nice, beautiful, symmetric spirals or spheres. They look like something has affected them, which leads us to think that colliding galaxies is one way to turn on an active galaxy. And so what happens, the basic idea here, this is kind of a long video, so I'll start it here. So what happens if you have two galaxies that get too close together, they eventually merge together into one galaxy. But while they're in the process of doing that, the gravitational effect that the stars can have on each other is pretty dramatic, and it causes the galaxies to look warped. And when this happens, a lot of the gas gets pushed around into weird shapes, and it gets pushed in toward the supermassive black holes at the center of each of these galaxies. And if there's enough gas that gets pushed into that region, then the black hole can start feeding. It can start eating, and it can turn on an active galaxy. Okay, so you can see here, as these galaxies continue on their little dance, there's these little bright knots here where those supermassive black holes are, and the gas and stars get shoved in to the middle. You can also see there's a lot of material getting blown out. That's another thing that happens when you merge galaxies. So there's a lot going on there. But effectively what you need is something to sort of mess up the distribution of gas so that the black hole has something to eat for a long time. And so colliding two galaxies together will often provide a food source for the black holes that we think lasts long enough that we see them as quasars or active galaxies. So I think that's a really pretty simulation. I think it's a really neat way to visualize what happens when you merge two galaxies. So the basic idea is that you have all these stars that are in orbit around the supermassive black hole, and when you merge the two galaxies, some of these stars get forced into orbits that put them too close to the black hole, and so they get eaten up. And eventually, all of that material does get eaten up, and you're left with only the stars that are in their sort of normal orbits farther away. And so then at that point, the active nucleus would turn off. So we actually think that the quasar, or the active galaxy, is actually a phase that galaxies go through, depending on what's going on in their environment. So now these phases last for millions or billions of years. So it's not something that we really expect to see in real time, sort of turning on and off very often. But we have seen some active galaxies that look like, at one point, they've gotten a lot dimmer, and they've lost some of their features that we normally associate with active galaxies. And so people think that they do sometimes turn off if you look at enough of them. So another really cool feature that I sort of glossed over, and I'm probably not going to spend a lot of time, more time on, is the jets that we see coming from active galaxies. So radio galaxies have these active nuclei at the very center, and they also have these enormous jets of plasma that shoot out, and these are coming from, the light that we see is coming from electrons that are moving at close to the speed of light. And so these jets are extremely large compared to the size of the active nucleus. And honestly, I just think they're really cool, so I kind of wanted to talk about them a little. But that's another common feature when people are talking about active galaxies or something like that. You might see something with a lot of jets there. So the idea is that we have these magnetic fields. So this is also a very active area of study. Okay, people are still working really hard to try to figure out how you shoot these electrons out at such high speeds. But the basic idea is that people think that we have these magnetic fields that get twisted up around kind of near the black hole. And all of that energy that's coming from the region close into the black hole is able to just push these electrons moving out at very high speeds. The details of that are beyond me, but there are some people who spend a lot of time coming up with trying to figure out exactly how that happens. And so we see these as some of the more spectacular active galaxies out there. So here's two of my favorite examples. So this image here, I think it might be my favorite. This is a combination of a Hubble Space Telescope, so optical image. So you can see stars. This is the galaxy here. And then the radio coming from the Very Large Array is being coming from these electrons. It's being shot out at high speeds, way bigger than the entire rest of the galaxy. So you can just imagine how much energy has to be involved to shoot this material out way beyond all of the visible stars in the galaxy. We have billions of stars in here, so this is not a small galaxy. And these radio lobes come all the way out here like that. And this is another example of this is a composite X-ray optical image radio as well that shows these radio jets that are being shot out from the center of a galaxy. So the active nuclei in these quasars and in these objects just have there's so much energy involved that they can produce these really dramatic, kind of amazing displays. So I'm running a little short on time here, so I'll just finish up with I wanted to talk a little bit about why we care about supermassive black holes, other than the fact that they're cool. And the reason for that is we see them in pretty much every galaxy out there. And we also see that there's a correlation between the size of the black holes and various properties of the galaxies that they live in. Okay, so for example, the mass of the galaxy's central black hole is closely related to the mass of the bulge of that galaxy. So the bulge is the very center, sort of spherical region of a galaxy. And so the mass of that bulge is correlated with the mass of the black hole. Now that might seem straightforward to you, but that doesn't actually have to happen, because the region over which the black hole has actual influence over the motion and the rest of the galaxy is actually really small. Okay, it really only affects the very center of the galaxy. But the whole rest of the galaxy knows how big that black hole is, which we see by this correlation. So this means these correlations suggest to us that there's some sort of connection between the way that galaxies grow and the way that their supermassive black holes grow. So in order to understand galaxy evolution and how the universe came to be the way that we see it today, we have to understand how supermassive black holes grow. So my area of research is using various methods to measure supermassive black hole masses in specifically active galactic nuclei. So specifically what I do is just make these mass measurements. And I also spend a lot of time trying to improve the way that we make measurements to make sure that they're right, so that theorists who are trying to use these black hole masses that we produce aren't doing it wrong, because we've gotten them wrong somehow. So I've used a variety of telescopes. This is the MDM 1.3 meter telescope up on Kitt Peak that I used for a good chunk of my dissertation when I was a grad student. And I'm currently using the data from the Sloan Digital Sky Survey, which is a survey running from Apache Point Observatory in New Mexico. And so this is the telescope here. And this image here shows one of their parts of the spectroscopic instrument that we use. So the instrument that we use, what it does is it tries to look at the colors of 1,000 different objects at a time. And to do that, they make these plates that have these little holes drilled into them. And each of those holes we plug a fiber in. And each of those holes corresponds to the location of an object that we want to look at. And so then what we do is we just point the telescope one time, and everything that falls within the view of this plate gets observed at the same time. And we get 1,000 different objects at the same time. And then we look at the colors of those objects to try to figure out what's going on. So, so that's what I spend my time doing. So I spend most of my time trying to measure black hole masses. So just to sort of wrap it up, supermassive black holes are found in pretty much all massive galaxies, and they're somehow connected with these galaxies. So that's why we care. other than the fact that they're just really cool. And we can measure their masses and learn about them by looking at the motion of material that's falling into them. So before it falls in, before it goes past that point where we can see it, we can actually use its motion to learn about them. And so as technology improves, we're getting better and better at figuring out what's going on close to these supermassive black holes, just like the very first image that came out last year. And so I think over the next decades, we're going to see a lot more things like that coming out, and we're going to be learning a lot more about what's going on. So this should be a really fun topic to keep watching in the news over the next couple decades. So I will end there. Thank you very much.
Thank you, Kate. We have time for questions. Vern.
Well, when you're getting the spectra of a galaxy from that plate, you're getting the whole galaxy. You're getting an awful lot.
Yeah.
So how does that tell you what the mass of a black hole is?
So what we do is we fit models. We know what galaxies look like without active nuclei. And so we sort of subtract a galaxy from that whole spectrum. We know what the spectrum of a galaxy looks like. We can separate that out from the spectrum of the active nucleus. We then use, this is a longer discussion, which I wish I had time to go into, but we then use a variety of techniques that use the variability of the material falling in to figure out how fast it's moving and how far away it is from the black hole. And once we get that information, then we can use that to measure a mass. So yeah, I wish I could have talked more about that today. I had to cut I was trying to figure out what I could cut out to talk a little bit about how we actually measure the black hole masses, but there's just no time.
Yes, on the those images you're showing with the jets of material go out in either direction, and I was just kind of wondering if maybe what we're calling or classifying as fast radial bursts, maybe we're just in a direct line of fire of one of those things.
Oh, so you've heard about these phenomena called fast radio bursts, which are these sort of unexplained bursts of radio emission. So the reason why we don't think that those are necessarily related to those jets, well, they could be related in some way, but the problem is that when we have those jets pointed at us, they're always pointed at us. And so what happens is when we're looking along the line of sight of those jets, we just get this constant flow of radio emission rather than those blips that are these fast radio bursts. And so it doesn't quite work. It just doesn't quite work out that those can be associated with what we call blazars. So there's an object called a blazar, and that's actually when the active nucleus is just angled toward us such that we're looking right along those jets, just by chance. We get a lot of radio emission and a very different looking spectrum. And so the fast radio burst phenomenon, I think just can't be that, because those are constant flows rather than quick ones. Yes.
So a long time ago, I read a PopSci article that stated that the singularity of a black hole can have different densities depending on the mass of the black hole. I always found that really curious. I don't even know what that even means, like an object of infinite density having, or an infinitesimal point in space having a varying density, and how like a supermassive black hole supposedly can have a really low density compared to a black hole of a smaller size or
Right.
smaller mass.
So the reason that happens is the physical size. So when they're talking about a density of a black hole in an article like that, what they're doing is they're taking the mass and then they're taking the size of the event horizon. And then they're just saying, using the sort of normal so the normal definition of like an event horizon. And they're using that as the size estimate. So the thing is that the event horizon size can, and this gets sort of into more complicated theory that I haven't I have not gone too deep into. But the event horizon size can vary a bit. And so I believe what they're saying is that at some point, when a black hole gets big enough, the size of the event horizon doesn't scale linearly with mass anymore. So it can get more massive, and it doesn't increase quite right.
The rule of thumb is that the radius of an event horizon is 3 times the mass of the black hole. If you measure in solar masses, your answer will be infinity. But that may not be true for supermassive black holes. That may vary.
Right.
But the singularity is you're dividing by 0, right? The density is infinite in the singularity.
Right. You also have when you're calculating densities, density is proportional to the radius cubed when you're talking about a spherical object. But it's also only proportional to the mass, to the first power. So it's mass over radius cubed is essentially what the density is. So the mass, even if they do go up linearly, the density is going to go down by quite a bit faster if the radius also increases linearly. Does that make sense? Just because there's a cube power on the bottom. So as you get heavier black holes, that density will go down. Now the thing is that when you talk about a density of a black hole, again, you're using this event horizon as a proxy for the physical size. Really, when you're talking about a singularity of black hole, you're talking about like an infinitely tiny point at the center. So there's sort of like a difference there. But when they're talking about the density of a black hole, that's usually what they're referring to is the density within that event horizon, if it were averaged out like across that whole area. Yeah, because it's not constant in there, right? So theoretically, all the mass is shoved into the very, very center. So that event horizon doesn't actually have mass spread out evenly within it, right? It doesn't have like a surface like that. All the mass is shoved to the middle. And so really it's that density that they quote is just the density. It has to be the average throughout the event horizon.
Yes. Given our Milky Way galaxy is going to interact with the Andromeda galaxy in 4 or 5 billion years, do we have enough information to determine how that interaction is going to happen or to model it accurately?
I think that people have been modeling how the Milky Way and Andromeda are going to interact someday. I think yes, because they have pretty good measurements of what trajectory Andromeda is in and what trajectory we're on, and then we know roughly how much mass is in each galaxy, so they can do pretty well. I'm not sure. I think that might be. Those simulations that do that are like take a lot of computation and a lot of details to run out. So I don't know. I haven't personally seen the simulations, but I would imagine that someone's done it. Does your Tina do it? Oh, is there? Oh, okay.
Yeah.
Okay, so it sounds like yes, and they're available to see. So if you Google this, I bet you can find some. But we do think that eventually the two will merge together. They'll do a bunch of pass-bys first. So
Any other
Andromeda and the
questions?
Milky Way will go back
We
and
have a
forth.
question over here. Could you pass this over to him, please?
Hi, thank you. You spoke earlier about what happens when a star or any matter gets close to a black hole,
Yeah.
and how it disperses out into space, and then part of it gets sucked into the black hole. I was wondering what happens with that extra mass that when it's put out into space, as far as like, is it solar radiation or like what would happen to masses nearby? Like say Earth was, I don't know, 100 million miles away, what would happen?
So the material that gets pulled in when a star or gas cloud or something gets too close, that material will all go in, but it does emit radiation on the way in. So we don't have like material being pushed out, although I guess in that simulation there was material being blown out, but that's a very different, that's a bigger scale issue. So the radiation that comes out, there's a lot of really high energy radiation. So if you were to put the Earth too close to something like that, it would get cooked.
Okay.
So we've actually, it turns out though, again, you have to get really close to it for that to be a problem.
Yeah.
Space is really big, and I think almost all of us forget that a lot of the time, because it turns out if you turn like the Milky Way black hole, for example, into an active nucleus, even at like the brightness of a normal active galaxy, which is pretty bright, at the distance of the Earth, it would look bright to us in the sky. It would be kind of look like a bright star, but it wouldn't harm us.
Follow-up question then, though, but solar flares, I've heard, can cause magnetic disruption
Yes.
within our field. So would
Yeah.
that have an effect as far as magnetic fields within our area?
So you mean like so are you still talking about a black hole that's
well, I guess I'm
farther than
talking
the
about,
sun, or are you talking about like,
Yeah.
yeah,
What if the Sagittarius A star
Yeah.
galaxy developed a magnetic jet?
right. So what if we were in line of like one of those jets instead of just the normal radiation? That's a good question. I hadn't thought about that one.
Usually they point out at 90 degrees.
Yeah,
Disk.
yeah,
On the disk, so hopefully it's not pointed at.
right. We would have to be very poorly placed because there's only like a small region really where that could affect us. We'd have to get really unlucky. But yeah, that might mess up with like the Earth's magnetic fields or something like that. I'm not sure. It might be low enough density by the time it gets farther out, because the jets still expand as you get farther away, and so the energy still gets spread out. So it might be that unless we were really close in, it would still be okay. But I would have to think. Yeah, I would have to think hard on that one.
Question here.
Yeah.
So the image that you showed from the EHT that made it to the New York Times.
Yeah.
So if I got you right, you said that the event horizon was 1/3 of the dark area we saw. And if I understood correctly, that the closer you go, you get the X-ray radiation. But in the image, why is it dark? Why are we not seeing anything there?
Okay, so yeah, when looking at that image, I'll just pull it up here so I can point at it. So the image of M87's black hole. We can't see anymore.
Yeah, I'll bring down the
All right,
lights.
that's okay. Oops, I'm losing my mic here. So the X-rays are actually still on a lot larger scale than what we're seeing here. So the X-ray, the accretion disk, the radio that you see in there is coming from the inner part of the accretion disk, but most of the X-rays and most of the accretion disk are actually coming from farther out. We don't see it in this image because this is just a radio image, and you get radio emission from in there too. So we actually don't really get anything at all. The accretion disk itself is on larger scales than what's shown in this image. That's correct. Yeah. Oh, so he was asking. So I said that this dark region in here was about 3 times the size of the event horizon of the telescope, and then we have this material here, which is radio emission. So he was asking, where would one find the X-ray emission that I had also talked about coming from the accretion disk around a black hole? And so the accretion disk itself is actually much larger than what's seen on this image. This image is really focused toward just the very center.
So how many supermassive black holes are there in the universe? Is this one per galaxy or
So
something
roughly
less,
one.
or
So there's roughly one supermassive black hole per galaxy in the universe. Some of the small dwarf galaxies don't have them. So billions. Some galaxies do have more than one. Galaxies that have recently merged with another galaxy, sometimes we see them before the black holes have had a chance to merge together. So there's a lot of people who are searching for those, who are looking for galaxies or active galaxies that have 2 separate nuclei.
Is there any limit to the size?
Any limit to the size?
Meaning the mass of the black hole.
Yeah. That's a good question. I think no. I think as far as I'm aware, I'm not 100% positive on that. I'm not a theorist, so there could be something that I'm overlooking here. But really the limit just comes from having the amount of time to grow it. So they've been growing for billions of years. The universe is 13.9 billion years old. So they just haven't had time to get bigger than they are. But as far as I know, I don't think that there's a limit. Or at least if there is, we haven't reached it yet as to how big the black holes can grow.
We'll take one more question here. One more.
It's two questions, sorry. Why are they so confident that it's an infinite density in a black hole? And if it's an infinite density and infinitely small, how can it spin?
So the reason why we are confident that it is an infinite density is because there is no known force that can hold up that amount of mass and that amount of, that can hold up something that is that dense. So when you have a star, for example, a star is held up by the radiation that it produces that comes out and it holds up the layers of the star. Now, if the star, when you go to something more dense, like a white dwarf, you now squash things down so that we actually have something like neutrons that are squished together, and there's this force, the neutrons resist being pushed closer together, so they resist the neutron star getting more dense. So it holds itself up just because neutrons don't want to get any closer to each other than that. Oh, I'm sorry, electrons for white dwarfs. I was talking about neutron stars. I skipped a step there. So anyway, neutrons for neutron stars. So they provide this little force. And the problem is we don't know of anything that can, once you get beyond that force that the neutrons exert, nothing can hold up anymore. Nothing is strong enough to resist that self-gravity. So like when something gets dense, it wants to collapse. And so there's nothing that can hold that up. And so since there's nothing that can hold that up, then the theory tells us that, well, it has to just keep collapsing infinitely until it's an infinitely small point. So does that help a little? Uh-huh. So I think the problem is at that point everything is so dense that it can't really sustain its structure like as a thing anymore. Does that? So there's nothing, like neutrons sort of hold themselves up like that, but then yeah, I think that's the best I can do with that.
Okay,
part.
we hope that you can join us next Monday night on March the 9th. You'll hear about the Dark Energy Spectroscopic Instrument, which is up on Kitt Peak. Telescope is closed tonight, but I'll stamp student assignments down here. Let's thank Dr. Grier one more time.